Nice. Okay, I'm going to tell you something about the developments in the PFAS removal from water. KWR is a water research institute, and so we are very busy with all kinds of treatment methods to try to get PFAS out of water. So why is this necessary? Well, first of all, I will show you the contents of this presentation. I start with the introduction. That's not a surprise, I think. Then I will tell something about traditional water treatment methods, how effective they are for PFAS removal, absorption processes, concentration of PFAS, degradation of PFAS, combination of techniques, and well, as usually I will end with some conclusions. So first introduction, well, I think or everyone who's attending has heard about PFAS. At the moment, there are more than 9,000 types of PFAS available. They are found everywhere on Earth, even in the most remote areas we can find PFAS. It's everywhere in our surface water, and unfortunately also very often it is encountered in the groundwater already. This is because these compounds are mobile, persistent, and accumulative, so they combine all nasty properties that a chemical can have. And a few years ago, it was found that possibly or probably they are toxic, and certainly more toxic than we thought they would be before. Now, for drinking water also contributes to the amount of PFAS that people consume. And to calculate the maximum PFAS concentration of water that would be acceptable, it is assumed that 20% of our PFAS intake will take place via drinking water. The others will be by breathing from the air, and mainly it comes from food. Well, based on this assumption, it was proposed that there's a proposed guideline of 4.4 nanograms for a weighted sum of PFAS. And in general, for this weighted sum, they look at these 4 PFAS. These are the most famous ones with 8 carbon atoms. They all have a potency factor, that means how toxic they are, related to PFOA, perfluorooctanocarboxylic acid. PFOS, the sulfonic acid, has a potency factor of 2. There are some others with a lower or higher potency factor. But at the moment, they are also talking about trifluoroacetic acid. Now, this is a strange type of PFAS. It is a PFAS according to the definition. It has a very low potency factor, which is nice because it hardly accumulates in living beings. But on the other hand, it is really present in micrograms per liter, whereas the other PFAS are only present in nanograms per liter in surface water. This one is present in a factor of 1,000 more. So even if the potency factor is a factor of 1,000 lower, it still contributes a lot. And because it's a very small molecule, we will see later on, it's extremely difficult to remove it. Now, what are the traditional water treatment techniques that are applied? Well, this is a general overview. So in the Netherlands, 60% of our drinking water is made from groundwater and 40% from surface water. For groundwater in general, the treatment is aeration, flocculation, rapid sand filtration, and possibly some disinfection. And for surface water, you need a lot more techniques to get safe drinking water. Also here, coagulation, flocculation is applied, sedimentation, rapid sand filtration, and disinfection, but also many other techniques can be applied, although that is not a simple water treatment technique. This is simple water treatment technique, traditional ones, for drinking water. You can also apply slow sand filtration, and within these slow sand filters, biodegradation plays an important role. But anyhow, none of these techniques is efficient for the removal of PFAS, just doesn't work. So we'll have to look at more advanced techniques to get rid of these compounds. And one of the most famous processes for removing chemicals from water is adsorption. And in general, and I think almost all drinking water companies in the Netherlands use activated carbon at all their production sites to remove all kinds of chemicals, but also color and taste from water. Yeah, here we can see a picture. This is from a drinking water company which has 6 production sites. Well, and what we can see from these graphs, there's a very fast breakthrough of PFAS. In fact, small PFAS like the TFA I just talked about, but also this should be FBA, they are not absorbed at all. They just pass the activated carbon filter. Larger molecules, let's say from C6 until C9, C10, they are very well adsorbed at the activated carbon. And by doing this, they will displace the smaller ones that in the beginning also had been adsorbed. So what you often see with PFAS is that in the beginning, these small PFAS are removed, so their concentration drops. But after a while, the concentration increases again because they are displaced, and it even may be higher than the influent concentration. But even for the larger molecules, we can see that at about 10,000 bed volumes, 50% already gives breakthrough, or there's a percentage of 50% breakthrough for each compound, whereas for normal contaminants like pharmaceuticals, pesticides, personal care products, that happens somewhere between 20 and 90,000 bed volumes. So this is much more, much sooner, which means that a drinking water company trying to remove PFAS by means of activated carbon would need more filters, longer residence time or higher filter beds, that would also help, higher reactivation frequencies, about a factor of 5 on average, faster, higher. Well, this is very expensive, and also reactivation of the carbon has a high environmental impact. So the environmental impact of the drinking water production would significantly increase by doing this. You can see the breakthrough at different bed heights. These are data from a Dutch drinking water company. This is the influent concentration, and here you can see at several heights how the breakthrough occurs. In the beginning for PFOS, which has C8, so it is adsorbed. In the beginning it works fine, but you can already see at 80 centimeters within a bed height, it will already break through very soon, and at the other heights, it will certainly follow. What happens when this activated carbon has been loaded with PFAS? Well, it is reactivated under a reductive atmosphere at a temperature of 800 to 900 degrees C. And the carbon manufacturers have published some papers wherein they state that during this process, the PFAS is mineralized, so fluoride is formed. We checked that at KWR Water Research Institute together with the University of Bath, because there they had the oven that we lacked. And we indeed could see that these bonds are being broken, so this works. Now, don't mix it up. I often hear people who say that doesn't work because burning PFAS only happens at temperatures above 1200 degrees C. That's true, but then we are talking about burning, so in an aerobic atmosphere. You never use an aerobic atmosphere and reactivation of activated carbon, but because in that case you would burn your carbon and nothing would be left. So that's why it helps. It's the reductive atmosphere that works. But burning also is a problem. So solid waste, taking it to a site to burn it is not a good idea for PFAS because it will be released in the environment again. It will not be removed. Now, at the moment, if you look at literature, there are lots of developments in the synthesis of various adsorbents, like new types of zeolites that are specifically designed to remove PFAS. Cyclodextrins can be used, modified clay. There are several types of it, but in general, they are not yet available on a large scale, or they have not yet been tested at full scale. So it will take some time before these can be used in actual full-scale drinking water treatment plants. Ion exchange resins are a little bit of an exception. They are available on large scale. You can use them. They are very effective because PFAS in general have this long perfluorinated tail, but they have a charged head group that can interact electrostatically with the resin. That works. And it works even better if there's a combination of interactions, electrostatic interactions and non-electrostatic interactions of the long chain with the resin itself. On the other hand, it does work better, you have a higher absorption, but it's much more difficult to reactivate it because reactivation is done by adding a high concentration of salt to remove this electrostatic interaction, but obviously you won't be able to remove this interaction. And that means that in general, these resins are not reactivated and they are for single use. And if you then start to burn them again, if you burn them, you will release the PFAS again in the environment. So this still is a problem at the moment. And well, they are very expensive.
May I make a short comment?
Yes?
There are, of course, facilities that can burn these at adequate temperatures to get rid of the PFAS and completely destruct, just not within the Netherlands.
Not within the Netherlands. They are, for example, in Antwerp, that's the nearest site where you can do that. Last year, it was there was something in the news that also they didn't fully burn it, and there were some illegal activities with it that they just discharge it into in the surface water. So yes, it can be done, but not in the Netherlands. Instead of absorbing it, you can also concentrate PFAS, for example, by using membrane processes. Nanofiltration is more effective than you would think based on the size of the molecules and the pore size of the nanomembranes. And this is also due to electrostatic effects. And reverse osmosis is very effective and can also remove small PFAS. But as usual, there are some disadvantages. The recovery of these processes is at the most 80% on full scale. So that means that you have to take in 25% more water. In some areas, this is difficult because there are water shortages. And at the end, you end up with 20% concentrate with a 5 times higher PFAS concentration. What to do with this concentrate? If you just discharge it onto the surface water, you will add the PFAS again. Another type of concentration process is foam fractionation. PFAS are very surface active, so they accumulate in foam. In general, you have to add some detergent, and in this case, a cationic detergent is most effective, but also more toxic than anionic detergents. It can be applied on a large pilot scale or even full scale already, but also in this case, this is our setup in the laboratory of KWR. But what to do with the foam? Because now we have a foam which contains high concentrations of PFAS. The most beautiful thing that we could do would be to degrade PFAS. Then we would get rid of these forever chemicals. But the advanced oxidation processes and normal oxidation processes are totally ineffective because the CF bond is much stronger than the CO bond. We cannot oxidize it. So that is a practical problem. There's a practical problem also with doing these experiments. I was a bit surprised by this problem when I encountered it. If you want to measure how effective your degradation was, you should be able to detect fluoride, F-. But we are talking about PFAS with a detection level of about 0.5 nanograms per liter. So we are looking at nanograms per liter concentration ranges, whereas the detection limit for fluoride is 20 micrograms per liter. So even if you degrade all the PFAS in surface water, you will never be able to reach 20 micrograms of fluoride. So that is, at the moment, that is a practical hurdle in determining the efficiency of your process. At KWR, we did some experiments with advanced reduction, so that's the opposite process from oxidation. We add electrons, and then you can cut off fluoride. These experiments have to be done under anaerobic conditions. They work best at pHs of 10 to 12. We tried several pH ranges. They are much more effective for the carboxylates, the red bars, than for the sulfonates, the green bars. So it has something to do with the head group. And unfortunately, what we also found, we also used a combination of sulfide and iodide that was more effective than using either one of those. But unfortunately, it's less effective for high salt concentrations. So if we are talking about applying this technique in membrane concentrate, then you will also have concentrated the salt salt. So then it's less effective. This problem will not occur in the foam fractionation. So then we turn to anodic oxidation. I said oxidation processes are not effective, but by anodic oxidation, by forcing it electrostatically, that works. Although you do need a special type of electrode, a DBD electrode. It is very effective, as you can see. You can see the effects of different reaction times. You can see that we can reach 80–90% degradation of PFAS. But this is on a small laboratory scale, and for large scale, mass transport to and from the electrodes will be a challenge. And what we also saw that here we are looking at the model compounds, but there are some transformation products formed. So we cut down one large PFAS in 2 or 3 smaller ones, and that also is not exactly what we were looking for. The largest advantage of this is that it is also applicable in concentrate. It's not hindered that much by salt concentrations, but yeah, not yet at full scale. We are still working on that. So at KWR, how do we think that it would be best to tackle the PFAS problem in water? Well, we think that the most promising strategy would be to apply a series of techniques. First, concentrate the PFAS so that we don't have to treat such enormous amounts of water, and then try to degrade it in a concentrated waste stream. So just use a train of treatment techniques. But well, still a lot of development will be required to reduce costs and environmental impact. And on the short time, I think filtration over activated carbon seems to be the most practical way to go forward, although it will mean that drinking water production, the operation conditions will change, and the environmental impact will increase, and it will be more expensive. Producing drinking water will be more expensive in this way. So this brings me to my conclusions. Well, PFAS are really present everywhere. They cannot be removed by using traditional water treatment techniques. They can be adsorbed into some different adsorbents. Some are very promising, but still in development. Adsorption onto granular activated carbon is partly effective, not for the very small ones, but it is for larger PFAS, but it requires about 5 times higher reactivation frequency. However, the advantage is that during this reactivation, PFAS seem to be mineralized, so in that case, it's an effective way to degrade it. PFAS can also be concentrated, applying nanofiltration, reverse osmosis, or foam fractionation. However, you will get stuck with a concentrate that will have to be treated further. Advanced reduction may be effective, but only under specific circumstances. And anodic oxidation seems to be more promising, as it can also be applied under more difficult circumstances, like in the concentrate. But overall, we certainly will need more research to remove PFAS on a very large scale for drinking water. Well, this was my presentation. So if you have any questions, feel free to ask them. And if there's no time, or if you want to discuss further, you can here find my email address.